Hello everyone, you're welcome to today's lecture on soil chemical properties, and today we will be covering part 2. If we can all remember, in part 1 we looked at the different types of soil colloids, and these were the organic soil colloids, which are humus, and then the inorganic soil colloids, which are the clay minerals. So today we will specifically look at the clay minerals, which we said have plate-like structures, like seen in the pictures below. So if we have crystalline silicate clays, for them they have different layers, and these layers are stuck together to form a book-like structure. We also see that the most important silicate clays are known as phyllosilicates, and these phyllosilicates are made up of two sheets. We have the tetrahedral sheets and the octahedral sheets. The tetrahedral sheets normally have silicon at the center, which is surrounded by 4 oxygen atoms, and it is called a tetrahedron because the oxygen atoms define the apices of the 4-sided geometrical solid that resembles a pyramid. We can also have different layers formed by these tetrahedrons sharing the oxygen atoms, hence forming different layers. The second one is the octahedron, and in the octahedron we see that we either have an aluminium atom or magnesium atom at the center, surrounded by 6 oxygen atoms or 6 hydroxyl groups. This therefore forms the 8-sided solid, which we call the octagon. In a similar way, the octahedrons can also be bonded by the oxygen or hydroxyl groups to form different layers. So now let's look at isomorphous substitution. This is a process by which one element fills a position that is usually filled by another element of a similar size. For example, in the tetrahedral sheets, we can have the silicon atom replaced by aluminium. Or in the octahedral sheets, we can have zinc replacing aluminium or magnesium, or aluminium replacing magnesium, or zinc replacing magnesium. Okay, so we can have any of these 3 at the center. Okay, so now let's look at the mineralogical organization of silicate clays. We see that this depends either on the number or the arrangement of the tetrahedral and the octahedral sheets that are present in that given soil. We have the 1-to-1 type minerals, and these 1-to-1 type minerals come about by having one tetrahedral sheet bonded to an octahedral sheet. So we have one of each sheet bonded together to form the 1-to-1 type minerals. The most prominent example of these minerals is kaolinite. Then we have the 2-to-1 type minerals, and these ones are mainly formed by having one octahedral sheet sandwiched between 2 tetrahedral sheets. For the 2-to-1 type minerals, we have those that are expanding and those that are not expanding. The expanding type includes the smectite and vermiculite, and the non-expanding type includes the mica, illite, and chlorite. This picture explains what we've just discussed in the previous slide, where we see that kaolinite has 1-to-1, one tetrahedral sheet and one octahedral sheet. And then the 2-to-1s, for example, the montmorillonite, the illite, and the chlorites also have one octahedral sheet that is sandwiched between 2 tetrahedral sheets. So what characterizes kaolinite clays? We see that in kaolinite minerals we have a very strong hydrogen bond, and we also see that these minerals don't allow water to penetrate between their layers, so they almost have no swelling taking place. We also see that kaolinite has a low cation exchangeable capacity, and we also see that it exhibits less plasticity or capacity to be molded, thickness, cohesion, and shrinkage. So therefore, because of these characteristics, kaolinite containing soils make very good foundations for buildings and also road beds for construction of roads. These are the different types that we've talked about: the expanding, including the smectite and vermiculite groups, and then the non-expanding, containing the micas and the chlorides. So now let's look at the sources of charges on soil colloids. The first source is that when hydroxyls and other functional groups on the surface of colloid particles release or accept hydrogen ions, there can be a provision of either a negative or a positive charge. Then 2, when we have an imbalance that is brought about by isomorphous substitution in some clay structures, we normally have either a positive or a negative charge created. For example, for the negative charges to be created, we normally have a cation with a lower charge replace a cation with a higher charge. For example, magnesium replacing aluminium. And then for positive charges to be created, we normally have substitution of cations with higher charges, for example, aluminium, with the ions or cations that have lower charges like magnesium. So if we have aluminium replace magnesium, then we will have a positive charge created. Like we earlier saw, in ion exchange we have normally different ions that are suspended in the soil solution replace the ions that are adsorbed on the soil colloid surfaces. Okay, so if the soil surfaces are negatively charged, then we will have adsorption of positively charged cations. Thank you so much for listening, and in case you have any questions about this topic, kindly send them to me through my email address or through the learning management system. May God bless you.